Hi, my name is Martin Siegert. I am Professor of Geosciences at Imperial College London and co-director of the Grantham Institute for Climate Change. Welcome to my exp. So I'm a glaciologist and I study how the Antarctic ice sheet flows and indeed what's underneath the ice. I predominantly use geophysics, and the geophysical technique of choice for me is radar. And the reason I use radar is because radio waves travel straight through cold ice, but they bounce off the bottom of the ice sheet. And so we can measure the two-way travel time of the radio wave. We know the velocity of the radio wave in ice, and so we can measure the ice thickness. If we know the ice thickness, we can measure the topography underneath the ice. And in both cases, Greenland and Antarctica, if you take away the massive ice sheets, and they are huge, by the way, there are over 3,000 meters thick in Greenland and over 4,000 meters thick in Antarctica, what you see is a very complex landscape, hidden, buried by those massive ice sheets. And it's the landscape that gives us concern in both places. And what we have in Antarctica is essentially two components of the ice sheet, a West Antarctic ice sheet and an East Antarctic ice sheet. The East Antarctic ice sheet is by far the biggest of the two, and most of it is resting on land above the level of the sea. There are amazing mountains and valleys and landscapes. The last mountain range to ever be discovered was the Gimburtsov subglacial mountains in the middle of the East Antarctic continent. It was only discovered a decade or so ago, just phenomenal. But if you go to West Antarctica, we see a different situation. West Antarctica is still a continent, but the level of that continent is below the sea level. And the ice sheet that's on it is grounded below sea level, which is unusual. And in some parts, it is over 2 kilometers below the level of the ocean. It's quite remarkable. We're really concerned about that from a glaciological perspective because it's seemed to be an unstable, potentially unstable situation where if you have melting at the edge of the ice sheet, then the grounding line, which separates floating ice from grounded ice, starts to migrate backwards into potentially deeper territory. And as it does so, the ice sheet starts to melt even further, and there's a runaway feedback process kicks in. This has been thought about since the 1970s, that the landscape in West Antarctica is like a weak underbelly. And if it starts to melt at the edges, we are very concerned that the ice sheet will become unstable and rapidly disintegrate. Now, in West Antarctica, that's enough ice to raise sea level by about 3.5 meters. In East Antarctica, there are parts of East Antarctica too, which are vulnerable to change. And again, it's those bits which are grounded below the level of the ocean. Most of it isn't, but there are parts of East Antarctica that are changing too. The issue with East Antarctica is that you don't have to lose an awful lot to have a massive effect on global sea level. It's got enough ice in East Antarctica to raise sea level by 57 meters or so. It's very difficult to see that there is direct action in the polar regions that can make any difference. We have to understand that the polar regions are changing because of our activity. Increasing carbon dioxide and other greenhouse gases into the atmosphere is warming the atmosphere, it's warming the ocean, and we're seeing the effects of that warming in the polar regions, and most notably, of course, with the large polar ice sheets. So the most important thing that we can do to stop changes in the Arctic and the Antarctic and those ice sheets is to stop emitting carbon dioxide. And we need to do that really rapidly. The problem is the level of CO2 that we are emitting is going up year after year. And somehow we have to stop that. We have to reduce our emissions to zero effectively within about 30 years' time if we are to keep temperatures to about 1.5 degrees centigrade above what they were before the Industrial Revolution. And that's about as good as we can do. We're already locked in. We're already 1 degree warmer than we were in 1850. There's not much we can do about that. We're kind of locked into another 0.5 degree centigrade. There's not much we can do about that as well. But scientists, atmospheric scientists, explain that we can stop it there if we reduce emissions to zero in 30 years' time. But if we don't do that and global warming continues apace, then those ice sheets in Greenland and Antarctica will start to melt even more rapidly than they are now, with huge consequences for sea level globally. In about the year 1900, the level of the ocean was going up about 1.8 millimeters per year because of the onset of carbon dioxide and global warming after the Industrial Revolution. By the middle of the 20th century, it was something like 2.2 millimeters per year. And now it's about 3.2 millimeters per year and going up as well. So the sea level is going up, and it's been going up consistently since around about 1850. But the rate of change is going up as well. It's accelerating. And the reason for that is due to a number of things. Firstly, as the ocean gets warm, it starts to expand. The water expands, and so the sea level goes up as a consequence of that. The glaciers all around the world, they start to melt and the sea level goes up. But here's the strange thing. If all the glaciers, the 300,000 glaciers that exist on the planet, apart from Greenland and Antarctica, if all those glaciers were to melt, the sea level would go up by 0.5 meters, 50 centimeters. If Antarctica and Greenland, those ice sheets melted, sea level goes up by over 60 meters.